So here are my collaborators. Roger Ma is a student of mine at Perimeter. Dianhao Zhang is a postdoc at Penn State, and Jen B from Penn State, and Meng Chen from Yale. Here are the references. The main reference is this one I wrote with Rochen last September, and there is one that we're currently working on. Hopefully, at least a year is right here. We'll see.
But the first teacher probably.
Thanks for the blessing. There's some down. Oh. What? Sorry. All right. Yeah. So apology for your third introduction to SPT today. Well, let me go through it quickly. So these are gapped, unique ground states of some local Hamiltonian. The correlation functions are all orange, exponentially decaying. So they are orange entangled in the sense that the ground state wave function is adiabatically connected to a trivial unentangled product state, aka the harmonic insulator. But the non-triviality lies in the fact that this adiabatic path that connects my non-trivial state to a trivial state has to break some of the protecting symmetries. Right. So as long as I have the symmetry, this path is not allowed. Furthermore, I look at the boundary of such states. There are some non-trivial gapless or long-range entangled boundary guaranteed as long as the symmetries is there. In fact, the non-triviality of the boundary is characterized by the hooked quantum anomaly. So famous examples, including the Haldane AKLT chain in one dimension. So you have the integer spin chain with some dangling spin half at the end, or the famous topological insulators in 2 or 3 dimensions, where I have some gapped bulk. The bulk just looks like an ordinary semiconductor, but if I have an open boundary condition, then on the boundary I have some gapless atomic modes. Okay. So these are all well known by now, more than a decade old, or nearly 2 decades. Sorry. So for this talk, I want to ask, what happens if some of the symmetries in my system are not there exactly in a very specific way? Specifically, I want to think about a disordered system. Let's say I put in some random impurity in it. The distribution of this random potential obeys some probability distribution. What happens if for each disorder realization, for each random potential, there's some symmetry that's broken? But if I average over all the disorder configurations, upon averaging, the symmetry is restored. Okay. So of course there are very real reasons to consider such symmetry. For one thing, all the lattice symmetries, if I give you an actual piece of rock in the lab, then if I want to talk about lattice translation, or rotation, reflection, and so on, those are all at best average symmetries in real life, because any piece of material will inevitably contain some dirt, some disorder. And of course, there are other contexts. For example, if I have a topological insulator protected by time reversal symmetry, then I can imagine putting in some magnetic impurities that locally break time reversal symmetry, but the direction of the magnetic moments, the random magnetic moments, are random. So on average, I still have a symmetry. So for this kind of average symmetries, you can ask, does the notion of SPT still make sense?
How do you define an average symmetry?
Yeah, I'll it's basically what I define, but I'll put in more equation later. Yeah. So very simple. Yeah. So that's one thing you can ask for the bulk phases, right? The kind of crystalline SPTs or people talk about, do they still make sense for real crystal, right, which have defects? The other question which you can ask is from the boundary point of view. So the boundary, as I mentioned, were characterized by a non-trivial 't-Hooft anomaly. So now you can ask, does 't-Hooft anomaly make sense if some of the symmetries involved are only true upon disorder averaging. And if both anomalies still make sense, well, what are their consequences? Do they still constrain the IR dynamics in useful ways, just like how usual to both anomaly helps us understanding strongly coupled quantum field theories? And, in fact, that's another motivation for me to consider this problem. It is a motivation, it's probably even closer to my heart, which is there are lots of strongly disordered, strongly interacting quantum critical phenomenon, but in real life, things like quantum Hall transitions, superconductor insular transitions, and critical spin liquids with disorder. Those are very much real thing, but they are just extremely hard to understand theoretically. We just don't have that many tools, and so it will be nice to extend the notion of dwarf anomaly, which is a powerful tool to think about things non-derivatively, and see what happens there. So that's another motivation. Okay, so now so that's the motivation. Now let me try to define the words as carefully as I can to you. So now just think about, instead of a single Hamiltonian, just like the usual ASPT case, let me think about an ensemble of local Hamiltonians. Roughly, I mean, you don't have to do this, but you can separate the Hamiltonian into a clean piece and some disordered piece. So OI is a local operator that's surrounded, that's defined around site I. I is the lattice site, and the random potential, this random field, is drawn from some probability distribution PV. The only thing at this point, well, the order 0 thing is I want the disorder to be short range correlated. They are more or less spatially independent. So I'm saying. So this is the spatial independence condition. And then I want to think about the symmetry of my problem. So there are two symmetries that I can think of. One is I call it exact symmetry, which is a symmetry, let me call it K, that commutes with my Hamiltonian for any realization of the disorder potential. Right? So that makes sense. Just like if I have a dirty metal, U1 symmetry is still an exact symmetry. Dirty symmetry. And then I have the average symmetry, let me call it G. So under this symmetry transform, for example, this O transforms non-trivial. So O is not invariant. Equivalently, let's say this random potential V transforms non-trivially under G. So it forms a non-trivial graph. However, I demand the probability distribution of the V, the classical distribution, to be invariant under this G transform. So that's what I mean by an average symmetry. And for most of the talk, except for one slide, I think, I'll consider the simplest case where the total symmetry is the direct product of the two. In general, it can be a non-trivial extension, but for simplicity, let's just think about it. Direct product. Okay. And I want to think about the ground state, the ensemble of the ground states of these Hamiltonians with the exact and average symmetries. Just like the usual ASPT, we don't want the symmetry, any of the symmetry to be spontaneously broken. That's also assumed here. Okay. So I've defined my ensemble and the symmetry, my symmetry. So now let me define what I mean by SPT in this context. Okay. So remember, for the standard case, you have a single Hamiltonian, a single ground state. You demand that single ground state to be short entangled. So here, instead, we have an ensemble of ground states. So I have a different ground state for each disorder realization. What I naturally do is to demand each ground state, psi I, to be short independent, so to be adiabatically connected to a trivial product state, if the symmetry are not respected. And there is a slightly stronger demand requirement, which is I demand the correlation length Ci, which it's a correlation length for this state psi I, to be upper bounded in the entire ensemble. So not only I want Ci to be finite for each state, I want the whole ensemble to have some maximum Ci. Yes.
Clarification. So when you say disorder realization, that just means a particular choice of the new.
Yes. Yes.
Okay. And this correlation length is not the correlation length That's the new I, new J.
No. It's for the state.
Okay, and that correlation length is fixed,
Yes.
right? That exceeds fixed.
Yes. Yes.
So I understand that you need to deal with the symmetry, but if the system is gapped, if you argue that because you're adding a perturbation, you're not going to change the the factor of correlation.
Right. So, right. If you start from a pure gap state and add small disorder, of course, this condition will automatically be true. But but it turns out, in order to get more interesting later, I want to be more general than that. So for those cases, this condition has to be put in my hand. Of course, you can go fancier. You can put a soft upper bound instead of hard upper bound. You say C can be arbitrarily large with exponentially decaying probability, and then you can study rare region effect and so on. I'm not going to do any of that. That just makes my life more complicated, possibly more interesting, but more complicated. So at this stage, let me be very simplistic and put a straight upper bound on it. And also one comment, if you've heard a previous version of my talk or read the paper I wrote from last year, the definition was actually more complicated there. So this is a simplified version, which makes subsequent discussions slightly different, but still as interesting. So this is a simplified version. So now I can think about like continuously deforming, just like what we do in usual topological phases. Let me continuously deforming my Hamiltonian, also the probability distribution, while preserving all the conditions I mentioned. So short range disorder, all this, the exact and average symmetry is not broken, and the fact that any state in my ensemble is short range entangled with the upper bounded correlation. Okay. And I define average SPT or ASPT as simply the equivalence cost of the states under such continuous deformation. So that's the definition of the rule.
It can define equivalent class.
Meaning if I have two ensembles that they can be continuously tuned to each other without breaking all the rules, any of the rules I listed, I count them as the same things. That's as a compact, we can say that. Yeah. Okay. Yeah. I'm not in particular. I'm not talking about adiabatic evolution. I want to avoid that language because that turns out to be not the helpful language here. So that's why. Okay. So that's the rule of game. But before I continue, let me just do a one-page digression, which is there is actually a physically different context where I can talk about the average symmetry and SPT. So the previous definition, I call it disordered average SPT. But another context where I can actually talk about exact versus average symmetry is for open quantum systems. If I have a mixed state in general, I can talk about symmetries that just hit from the left and get an eigenvalue, or I can talk about symmetries that has to conjugate to the density matrix to leave the density matrix invariant. In fact, if I organize the previous ensemble I mentioned, I discussed into a density matrix, this is what how the exact and average symmetry behave. But the rule of the game is very different. So there, I have an open quantum system. I don't have the notion of Hamiltonian. So instead, the notion of deformation, the most natural notion of deformation, is to think about some symmetric finite depth channels. So the physics is obviously different, even though the mathematical structure is sometimes can get similar. So so I will not talk about this, but I think some of the other speakers may touch upon this later.
So for average symmetry, she commutes with the limit box operator.
Yeah. Yeah, the exact symmetry will be stronger. It will be like computing with the individual. All right. So so back to the disordered average SPT. So I gave you a definition of what these are, but just as usually how we think about the SPT phases, the definition per se is not extremely useful to work with, right? You have to think about all possible deformation path, which is complicated. Instead, we look for some topological invariants, and the most natural topological invariance that's generalizable to interacting system is the notion of topological response, right? So the idea is simple: is that just let's think about a usual SPT, let's say an integer pole. So a non-trivial topological response is basically saying that if I have some symmetry flux, if I imagine coupling my system to some background gauge field, then the flux traps some non-trivial symmetry charge. So flux traps charge. That's basically what a topological response is. The most well-known example is the integer pole effect. There, a quantized unit of the U1 flux traps some integer U1 charge. So that's the nice thing about thinking about this, thinking that way is that you can be strongly practical to begin with. You don't need free framing a picture. Okay. So the idea is just to do that, except now for average and exact symmetries. The thing that you immediately notice for average symmetry is that charge is not well defined. Or by definition, my individual states in the ensemble, they're not even symmetry eigenstate for the average symmetry. So you can't talk about charge. But the key thing here is that flux can be well defined. So symmetry flux can be well defined even for average symmetries. You can take some very simple example. Let's say you take some Ising model, some real scalar with a Z2 symmetry, but then you make the Z2 symmetry only true on average to turn on some random field in space. The notion of for a Z2 symmetry, the notion of symmetry flux is really just anti-periodic versus periodic boundary condition. So it's really just some boundary condition twist, and that is still well defined. Even in the continuum. In the continuum theory, the way to define that is to say, okay, my scalar field changes sign with the anti-periodic boundary condition, but I also demand my random field to be anti-periodic, and that's it. And then you just proceed. So the average topological response is, roughly speaking, is simply that I have an average flux. Well, you cannot trap average charge because average charge is not defined, as I explained, but it can trap some exact charge. And that's basically what it is, right? There's some average topological response. Of course, if you are nerdier, you replace the word charge by some invertible states in the corresponding dimension, and you get the response here. Let me offer you a complementary point of view. It's basically talking about the same thing, but in a slightly more concrete language. So this approach is known as the decorated domain wall approach in the study of the SPT. So let me first review the standard version. Standard version says that if I want to construct SPT, what do I do? Well, one strategy is to start from some G breaking state. Let's take a concrete example. Let's say I have some SO3 cross Z2 symmetry where Z2 is a average symmetry. Sorry, no, here, sorry. Just SO3 cross Z2. We're not averaging anything here. So I can start from some Z2 symmetry breaking state. That's just some Ising ferromagnet. But then to construct a symmetric state, and the standard way to do that is to let the order parameter, the spins, fluctuate between up and down and quantum superpose all different configurations. The only thing non-trivial here is that you can, within each domain wall, let's do it in 2 dimensions, so the domain wall is 1-dimensional object, you can decorate some more non-trivial state. In particular, you can decorate a lower dimensional SPT, let's say 1-dimensional SPT, for example, with the other symmetry SO3, right? So SO3 has a famous one-dimensional SPT known as the Houdin AKLT chain. So let's just decorate that. And then once we have the domain walls and they're decorated, we can condense the domain wall by forming quantum superpositions of different domain wall configurations. Okay, something like this. If you do it right, you get a totally symmetric state that gives you a non-trivial SPT.
Why is there a plus minus? The second is plus.
Yeah, in fact, yeah, that's another thing I should say. When you do superposition, of course, you have a choice of relative phase factors. And in order to get a short-range entangled wave function, in order to make sure that all your correlation function in space are exponentially decaying, there are some conditions put on the possible choice of phase factor. Turns out for this simple case, this kind of plus minus sign this correspond to two legal choices, and the minus sign is minus when the number of domains. I think the number of domain walls is, well, in this drawing is even. Okay, so it's counting the parity of the number of domain walls.
The sum is only over decorated domain walls.
Yeah, you draw all possible domain wall configurations, but every domain wall has to be decorated uniformly. Otherwise, the resulting wave function again doesn't look short range. Okay. All right, so once you have that picture in mind, oh, by the way, I should say that the connection between this picture and the previous slide about flux trapping charge is that the domain wall can be, you can think of the domain walls as basically mimicking a background gauge flux, right? Well, in fact, if you're putting a background gauge flux, it's essentially forcing in some non-trivial domain walls. Okay, so now for average SPT, it's a very similar picture, except the domain walls don't move, right? Well, what I mean by that. So for each disorder realization, the domain walls are given by the disorder, right? So I have some, let's say I have a Z2 random field, or there's some place where the random field points up, some place points down. Once that's given, okay, that's your domain wall configuration. So you don't get to choose. But there is a notion of domain wall proliferation, because as long as my ensemble has the average symmetry and the average symmetry is not simultaneously broken, the domain walls will proliferate, but not as a quantum superposition. They proliferate at the level of classical probability, right? So essentially, what you end up getting instead of a quantum superposition like this is an ensemble where there is some probability for you to get this configuration, and there's some probability for you to get this configuration, and so on. But the fact that you have the average symmetry means that as long as your length scale is large enough, any configuration, any domain wall configuration you draw has some probability of realization. And on this domain walls, you can decorate lower dimensional SPTs. For example, if I have now an SO3, exact SO3, and an average Z2 symmetry, then I can still talk about decorating on this average Z2 domain walls with the exact SO3 SPT, the Houdin chain. That still gives me a non-trivial state. Okay. So that's, so there I was mainly emphasizing the similarity between the usual SPT and the average SPT. But in fact, there are some important differences. One difference that's kind of immediately popping up is that this phase factor that I explained doesn't appear anymore, right? Because the proliferation of the domain wall is at the level of classical probability. So there's no such a thing as phase factor. So so this information, which is actually part of the important data to define the usual SPT, is now missing. And the example of a non-trivial Z2 symmetry SPT is known as the Levin-Good state. The wave function is basically all the configuration, the superposition of all the configuration of the Z spin but weighted by a phase factor that's -1 to the number of domain.
So on the previous slide, I should think of that picture as just like a density matrix. Then?
You can. The reason I didn't use the word density matrix is that in addition, it's endowed with the structure of Hamiltonian. Yeah, but very roughly, you can think of it as so that phase factor information is gone, and also there's a subtle point which it's an actually very interesting point which that's in our upcoming paper, but I don't have time to justify it fully. That's the statement that if I'm decorating with 0 + 1d G defects with a K symmetry charge, in fact, it doesn't produce a non-trivial average SPT. So I'm not going to explain it fully, but I'm going to give you a helpful analogy, which is the statement that if I have an atomic insulator with charge U1 conservation and lattice translation symmetry, well, that's classified by Z. That's basically saying in each unit cell, I have some integer charge sitting there. Now, once I add this order to make the translation symmetry only true on average, there is a way to smoothly interpolate between different charge fillings. The intermediate state will just be some Anderson localized insulators. Okay? So the existence of Anderson insulators means that such 0 + 1d decoration with some charge doesn't give non-trivial phases.
By atomic insulators, you mean tiny insulators?
It's worse than that. Atomic really means that you literally have just one electron sitting at each side, not moving at all. So the wave function is a product state. Yeah, it's the extreme limit. Right. And in fact, those what I described can go into a more systematic mathematical framework. So within group cohomology for bosonic average SPD state with this direct product structure.
Sorry,
Yes.
can I ask about the analogy in the previous slide?
Yes.
So why is that an analogy?
Yeah, so you can say what is one way to think about the atomic insulator is to say that I have translation symmetry and I have my translation symmetry defects, which are point defects. That's just my unit cell. So the number of the atomic insulator is labeled by the integer charge within each unit cell.
Oh, I think,
So that's a 0 + 1d
okay, I think
decoration.
that atomic insulator with different filling of the band or can be considered as different topological insulator.
Usually with exact translation symmetry.
Yeah, with the exact translation.
Now with average translation symmetry, of course, we know they are.
Yeah, they can all be connected.
Yeah, that's the. Yeah, so now within group cohomology, this is the classification. If you are familiar with the story of group cohomology, you will notice that it is more or less, it is almost the same as the usual group cohomology classification of bosonic SPTs, which is H upper D + 1 G cross K with U1 coefficient, except there are two missing pieces. So the P equal to 0 and P equal to 1 terms are absent in this Knuth-like formula, and the P equal to 0 piece correspond to exactly this kind of superposition phase factor. And the P equal to 1 information is exactly those 0 + 1d charge decorations that are trivialized by Anderson-like insulators. And all the other decorations, they are still non-trivial there, and they form non-trivial states, and they give you this classification. And if you are more general, let's say if you have fermions, or if your group structure is not a direct product but a non-trivial group extension, you can there are more general mathematical tools involving the Atiyah-Herzbruch spectral sequence. But I'm not going into that. I'm just telling you that there are mathematical tools that you can run to look to get some classification. But the classification to me is interesting only if it gets you some interesting new faces. So here is one. So this is an example that I call intrinsically disordered average SPT. So the previous picture, it seems to suggest to you that I just have less SPT with average symmetry than with exact symmetry, right? Because it's just some, it's pretty much the usual SPT, except some faces don't count anymore. Well, here's one that's the opposite. Let me take a fermion system, a 3+1D fermion system, where the symmetry, the only non-trivial global symmetry are all average symmetries, some Z4 cross Z2 average symmetries, and then the fermion parity symmetry. And I declare a domain wall decoration pattern, which is on the intersection of the Z4 and Z2 domain wall. But in 3D, each of this domain wall is a two-dimensional plane. So on the intersection, you get a one-dimensional defect. You decorate a Kilhai chain. You have fermions, you can do that. So in the usual clean SPT story, where the Z4 and Z2 are exact symmetries, this decoration is forbidden. This decoration is known that this decoration cannot give you a short-range entangled wave function. In fact, the minimum decoration that can give you a short-range entangled wave function is to decorate two copies of Kilhai chains on such domain walls, and that's actually a pretty famous state. It's known as the intrinsically fermionic and interacting SPT. But this single Kilhai chain decoration is forbidden. And it's forbidden because of an obstruction in one higher dimension. Essentially, what happens is that if you manage to have such a decoration, you should roughly speaking, you should think of the state as having some emergent anomaly. The anomaly corresponds to an SPT in one higher dimension, in this case 4+1D, with the Z4 and Z2 symmetry. But as I just explained, when all this symmetry becomes only average, well, this H_5 is just describing the phase factors between different domain wall configurations, which now becomes meaningless in the context of average SPT. Yes.
In the claim limit, the reason this obstruction cannot be that is because the Kilhai chain has VA classification.
Well, the Kilhai chain doesn't have VA,
No, yeah, right.
but maybe you can enlarge the symmetry a little bit to see it that way. The more standard way is to say if you have domain walls, they move around each other because of the Kilhai decoration, it gives you some inconsistent Berry phase. And the thing here is that now we have only classical superposition of the domain walls. The Berry phase no longer matters. Yeah. So this obstruction actually becomes trivial for the average symmetries. So in fact, this decoration does give you a non-trivial average SPT state that doesn't have a clean limit. If you try to push to a clean limit, it's not an SPT. So in some sense, this is like less is more, because we start by having less state for the average SPT than the usual SPT, but because there are less states, there are less obstructions, and that allows the existence of more non-trivial things. Okay. All right. So finally, let me also quickly tell you what happens on the boundary, right? Because as I mentioned, one important motivation to study SPT is because, well, even though they look pretty boring in the bulk, they are interesting on the boundary. The boundary has to have anomaly, which requires your IR dynamics to be non-trivial. So you can ask, okay, so suppose I do have some non-trivial bulk, do I necessarily have some non-trivial boundary dynamics? And the answer is yes, but in a slightly more subtle way. Yeah, I think I can go. Okay, so let me use the previous example of the exact SO3 times the average Z2 SPT. So remember, the picture is that on each Z2 domain wall, I decorate an SO3 holding chain. And I explained to you the picture on a closed manifold. Now suppose my system has a boundary. So imagine this is my system. Suppose, right? Let's argue in contrary. Let's say, suppose I have some disorder realization that such that even in the presence of a boundary, my entire system is short range entangled with some finite correlation length. Okay. In fact, you'll see that there's nothing forbidding you from doing that. There could be disorder realization that give you boring plus boundary. But what will happen is that now we can think about other disorder realizations with pretty much the same probability of realization. In particular, you can put in a domain wall here. You can essentially flip all the Z2 spins, all the random Z2 fields inside this domain wall, inside this domain, and then ask what happens. Well, as I said, once you create such a domain wall, on this domain wall there's a SO3 Hall chain declaration. But when this domain wall hits the boundary, at each intersection, well, you have a holding chain. So you have an open end with a dangling spin half moment. That's what a holding chain does. But now, if by assumption my original state before I flip the random fields inside, they are short range entangles. So regions far away from this domain wall should not basically not know what I did. Right? It doesn't know about the domain walls and doesn't know about this spin half moment. So for the whole state to still form an SO3 symmetric state, the only thing I can do is to let these two spins couple to each other and form a singlet. But that introduces a long range correlation or long range entanglement if this domain wall is large enough. And furthermore, there are infinitely many ways to create such long range singlets. Right? I can draw the domain wall here, I can draw the domain wall here, I can draw multiple domain walls. In the thermodynamic limit, there are infinitely many, in fact, it's exponentially infinite many ways for me to draw different domain wall configurations. So the statement is that even though it's in principle possible for me to find a disorder realization with short range entangled ground state, there are infinitely many more disorder realization with pretty much the same probability of realization that gives me longer range entanglement. Right? So the equivalent way to say that is that in my entire ensemble, short range entangled boundary state can appear with at most a vanishing probability, right? Vanishing as my system size goes to infinity. So it's this in this probabilistic sense that a non-trivial bulk guarantees a long-range entangled boundary. Of course, anomaly doesn't happen just on the boundary of the ASPT. I mean, otherwise you would have been more restrictive. Even systems on its own can have non-trivial quantum anomaly. Probably the most well-known example of dependence matter physicists are lattice systems with Lipschitz-Matisse constraints. So these are, for example, take some spin system with a spin half per unit cell. It doesn't have to be SO3, but any Z2 cross Z2 is okay as long as it gives you a projective rep. So this kind of system is known to have mixed closed anomaly between the SO3 or whatever exact symmetry you put there and the translation symmetry. So our result is basically saying that such mixed anomaly still makes sense even if the translation symmetry becomes only true on average. Right? In fact, in the special case of K being SO3, this was figured out in an earlier paper. It was shown that if I have a 1D SO3 spin chain with only average symmetry, but with spin half moment per site per unit cell, the correlation function has to be non-trivial. Okay. And in fact, for the spin half chain, if you're familiar with the random spin half chain, what the picture I described here is very much the picture of the so-called random singlet state. So that's a classic example. All right, so I think that my time is pretty much up. So to summarize, SPT and anomaly still make sense with average symmetries. The structure is similar, but not completely the same as the usual story. You can still understand them very fruitfully by thinking about topological response and decorated domain wall picture. There are also funny intrinsically disordered average SPT states that don't have clean limit, they don't have clean counterpart, and you have the anomaly, and the anomaly guarantees you long range quantum entanglement in a statistical sense with probability 1 approaching 1 limit. That can be used to think about LSM like this one. There are more things to explore, SET, various funny quantum phase transitions or disordered systems that are, that's for the fun of future. Yeah. And with that, let me just stop here. Thank you.
We have 10 minutes for questions, so. Yeah. If I have a clean system with the decorated domain,
Okay, so does that mean if you have what?
a clean system with a decorated domain or SPT where the decoration is in a lower dimensional manifold, and the boundary has some type of mixing anomaly between two symmetry. Now I average out one symmetry that would be average SPT.
Yes, only if, but provided the decoration is in higher than 0 dimension. Yeah, so I specifically picked this example because this potential is 1D. If it's 0D, it's not there. Yeah. So yeah.
It's a bit of a naive question, but in this decorated SPT construction, domain construction, the edge modes are the thing that you use to decorate themselves.
Yeah.
Is that right?
Yeah. Yeah. Yes.
And that's a totally general construction that
Yeah.
works for all kinds of SPT.
Yes. Yes. Yeah. I mean, that is a very general way to think about it. The only thing slightly more non-trivial is in the most general setting, you don't stop there. You have to look at whether your decoration pattern is really legal by working out all the obstruction, but that's always a good starting point.
I see. And that is also true for the average.
Yes.
Can you elaborate on what this would look like for a quantum Hall case? You
Oh.
mentioned that there you would define
Yes, for quantum Hall, we're still thinking about the exact implications. They are trivial implications, trivial in the sense that it doesn't require all this thing. For example, at the plateau transition, there is some emergent particle Hall symmetry. It's an anti-unitary particle Hall symmetry, and that's an average symmetry. And that is also known that it has a mixed anomaly with the U1 charge conservation. Unfortunately, the consequence of that anomaly is pretty trivial. Just saying your Hall conductance is 1/2, which we know anyway. Of course, if you go to multi-flavor, it's slightly more non-trivial. But long story short, from that perspective, we haven't gained anything new yet. So yeah, it's something that I still think about. Yeah.
I think you probably answered at some point, but I'm just really interested. So can you give a definition of an average anomaly? Just in a more maybe field theory sense.
Yeah, the field theory sense is that, yeah, okay. I didn't talk about how to think about this in a more traditional field theory sense. One thing you can do, for example, is to think about the replica field theory. And once you write down the replica field theory, it's manifestly symmetric. It has the manifest G symmetry, right? So nothing forbids you from coupling it to a background gauge field, and then you can integrate matter and get the response term and all the standard thing. The only thing non-trivial there is that because it's quenched in time, time component of that gauge field is trivial. That has, that leads to many of the things here. So there are things you can play there. The reason I'm not doing it that way here is because it turns out once we go to more general settings and so on, it became clear that that's not the most convenient way to think about the problem anyway. All this picture is still generalized to general settings. Yeah.